And now let's substitute the boundary condition into it. Boundary condition, again, looking at the local reference, x2 and y2. This is true for local coordinate systems at x2 and y2. x2 and y2. Not with respect to x1, y1, but only with respect to x2, y2. So when we establish that kind of boundary condition, of course, at this region, there's no displacement. So this is essentially based on our reference coordinate systems definition. Now, what about the slope? What about the slope at the, because we always use the slope condition, right? What about the slope at 0, which is at point B? What do
going to be the slope at y1 prime at x L over 2?
Yes, very good. Thank you. And the last one is what? Is the deflection condition when y2 is at the end, which is L over 2. This is the displacement condition. The deflection is delta C minus delta B, which is one we have written before. Now we record it again, right? We already have this one before, which is this right here. Now we're just using it. So I'm not going to go through the math because I think that you can figure this out. So by plugging in these boundary conditions, we can find out these coefficients. And the coefficient C turns out equals to MA over EI K1, K2 times sine KL over 2. And coefficient D turns out to be negative MA over 2P times cosine K1. Actually, this should be careful here. This is K1 for the C because it uses the continuity condition. Careful. This is K1 times L. And cosine K1 over L by 2 plus MB over 2P minus MB over P. Now, of course, you know that the last two terms can be combined. And one more thing, this kind of condition is what we call continuity condition. Which will further explore it in other examples in the future. And next one is step 4. Step 4. Once we have these two expressions, now we have the expression of y1 and y2, so we already have that. You can say that with y1, y1x1, expression of y1x1 and y2x2, we also have the following. We also know that when y1 at L over 2, deflection is just delta B. And when y2 at L over 2, this is just delta C minus delta B. Right? And we also know that MA equals P times delta C plus delta B. And we also know that MB equals P times delta C minus delta B. Right? So with these expressions, you can replace these terms. Replace them, which is in the coefficients, because we have not replaced them yet. You can substitute these conditions, which is expression of MA and MB into here. MA, MA, MB, MB, right? So in the end, all these MA and MBs will be replaced by the expression of delta B and delta C, correct? Because after this substitution, there is no MA and B. Everything is in terms of delta B and delta C. Okay. So then we're going to write the whole thing this way. We're going to write that when you plug in this L over 2 into the expression of y1 of x1, we're going to say that let the y1, this expression, minus delta B, which this expression is also delta B, delta C dependent. When you write this, this equals 0. So this is just rearrangement of the first expression I gave you here. And similarly, the second expression is we're going to write y2 at L over 2. We're going to write it y2 of L over 2 minus delta C minus delta B. This should also be 0. Once we do it, we're going to have two expressions, and they're all in terms of delta B and delta C. Correct? They'll only be depending on delta B and delta C. There's no more MA and B because of the substitutions of these two. Once you plug this into y1 and y2 expression, there's no more MA and B. Everything is in terms of delta B, delta C. What we're going to do is just like the approach that we did in the last example. We're going to write the whole thing in the matrix form. So we're going to take everything, rearrange everything based on delta B and delta C. So if you do that, these two, this one can be written as this expression. Here, the first expression can be written as this. We're going to call it coefficients. We're going to coefficients K11 times delta B plus K12 times delta C. This will be 0. And the other expression, we will call it K21 times delta B plus K22 times delta C to be 0. Of course, this could be a good exercise for you to practice. How do you get expressions of K1, K2? For these coefficients, K1, K11, K12, K21, and K22. All you have to do is just to substitute x1 with L over 2 and x2 with L over 2 into the expressions that we have found before. So once you've done it, you can just get this one. But this is just mathematical substitution. I'm not going to repeat that process here. And once you have this, remember the way is to separate delta B from delta C and rewrite them in matrix form. If you can have these two expressions, you can just write the whole thing in this format. That means K11, K12, K21, K22, times delta B delta C equals 0, 0, like this, right? Like, you still remember what we did last time? We said that because delta B and delta C cannot be 0. Why they cannot be 0? Can anyone tell me that why they cannot be 0? Anyone? Yes.
Is it because there are displacements that are not at the base of the beam of the column?
Not quite. But think about that. What will be the case when delta B is 0?
There's no load.
Right? There's no load, right? When there's no load, delta B is 0. What's the case when delta C is 0?
There's no
There's no
load.
load, right? So what's the case with when delta B equals 0 and delta C equals 0? That means there's no force. The colony is just quietly sitting there, minding its own business. And then it loses the whole purpose for us spending so much time trying to find out the solution of this column, right? So it has to be the case that delta B and delta C both cannot be 0. Otherwise, you become what we call trivial case. So that's the reason. Not because it's not at the center, because it just cannot be 0. If it's 0, there's no force. And if they are not 0, and that will lead to one condition. That means the determinant of this matrix, which I'm not going to copy the whole thing, must be 0. So what's the determinant of this expression? We did this before. You already know that. That means K11 times K22 minus K12 times K21. This must be 0. This becomes our characteristic condition for finding the buckling. And next page, 5. Okay, here. So this is page